Let's imagine that we're doing an experiment that is very sensitive to pH. And so we need to make a solution that will resist any changes in pH so that we have a constant pH throughout our experiment. Imagine that we want this pH to be 7.2. How would we make a buffer system at pH 7.2 with a strength towards addition of strong acid and strong base that is at least 0.05 molar? That is, we can add at least 0.05 molar of a strong acid or a strong base and still have the pH remain close to 7.2. There are several questions we would need to answer in order to figure out how to make this solution. First of all, we need to know what acid should we use. Then we need to know what ratio of acid to conjugate base would we need to achieve the pH of 7.2. And then what concentrations of acid and conjugate base should we have in our solution. And then from that, we can determine what the analytical concentration of acid is in our final buffer solution. To answer our first question, we need to remember that acids will buffer best near the pH that equals their pKa. So acetic acid will buffer around 4.7. That's pretty far away from 7.2, and so acetic acid would probably not be a good choice. Carbonic acid buffers well around a pH of about 6.4. That's a little closer to 7.2 and might be in the running, but hypochlorous acid would buffer best around 7.5, which is quite close to 7.2. And so if we were choosing, we would probably choose hypochlorous acid. Next, we want to determine the ratio of acid to conjugate base that we need in order to achieve our final pH of 7.2. To do this, we go back to our equilibrium equation and recognize that hypochlorous acid in water is going to ionize to form the conjugate base plus H3O+. And so the Ka expression for that equilibrium is H3O+ times the ClO- divided by the HClO. We know the pH that we want, and we know the Ka because we have the pKa. And so we can rearrange this equation. Ka divided by H3O+ is equal to the conjugate base concentration divided by the conjugate acid concentration, or the ratio of conjugate base to conjugate acid. Notice that if I take minus the log of both sides of this equation, I will get the following. Remember that minus the log of one quantity divided by another quantity is the log of the top minus the log of the bottom. And so I have minus the log of Ka minus the log of H3O+ is equal to minus the log of the ratio of conjugate base to conjugate acid. Now we recall that minus the log of Ka is pKa, and minus the log of H3O+ is the pH. And so we can write this as pKa minus pH is equal to minus the log of the ratio of the conjugate base to the conjugate acid. And our pKa is 7.53. So we have 7.53 minus the pH that we want, which is 7.2, and that is equal to 0.33, and that is equal to minus the log of the ratio between the conjugate base and the conjugate acid. And so if I take the minus sign over to the other side, minus 0.33 is equal to the log of the ratio that I want, ratio of conjugate base to conjugate acid. So now I need to take the inverse log of both sides. So 10 raised to the minus 0.33 will equal the ratio I'm looking for, which is the conjugate base to the conjugate acid. And that is equal to 0.468. So at this point, we've answered two of our questions. We're going to use hypochlorous acid, and we want a ratio of conjugate base to conjugate acid that is equal to 0.468. To answer the next question, we remember what happens when we add strong acid or strong base to a buffer. If I add strong acid, that strong acid is going to react with the conjugate base that I have present in solution. And so if I want to be able to add at least 0.05 molar of strong acid, I need to have at least, if not more, 0.05 molar of the conjugate base in solution. Likewise, if I add a strong base, it's going to react with the conjugate acid that I have in solution. And so if I want my buffer to resist changes up to 0.05 molar addition of strong base, then I need to have at least 0.05 molar of the conjugate acid in solution. So if I rearrange my ratio, I can see that the concentration of conjugate base needs to be equal to 0.468 times the concentration of the conjugate acid. And so I need to have more conjugate acid in solution than conjugate base. So I need to have at least 0.05 molar of each. So I should have at least 0.05 molar of the conjugate base, and then I can have more conjugate acid to make sure that my ratio is 0.468. And so I'm going to set my conjugate base concentration to 0.05 molar because I need to have at least that much in solution. And that's going to be equal to 0.468 times the conjugate acid concentration because I need to maintain that ratio of 0.468. And so if I then solve for my conjugate acid concentration, I will have 0.05 molar divided by 0.468, and that will give me 0.107 molar of the conjugate acid. So if I make my solution 0.05 molar in conjugate base and 0.107 molar in the conjugate acid, I should have a buffer that is at pH 7.2, and it should resist changes in pH to addition of strong acid and strong base up to at least 0.05 molar. So these concentrations are the answer to our third question. Our fourth question is, what is the analytical concentration of the acid in the final buffer solution? These are the concentrations in our final buffer solution, and the analytical concentration is just the sum of those two concentrations. And so the analytical concentration, the sum of the conjugate acid and conjugate base concentration, which is 0.157 molar.